Okay, here we are. I'm going to be talking about the second part of the fluid mechanics lectures, which is one of my favorite topics, so I hope that shows. And before I get too far with this, the first thing I want to do is, so the following is true of the Survey and Jewett homework. So this may not necessarily be true for the OpenStax homework, but Survey and Jewett assumes that atmospheric pressure is 101.3 kilopascals, so very close to 10 to the fifth pascals, but just a little bit extra. And because they're trying to get to make sure that you get it exactly right, they're looking for make sure you get it within a few percent. This conceivably could throw you off just enough. So I'm going to have to check what it is on OpenStax, but if you're doing Survey and Jewett, which we're still going to use in the spring semesters at OSU Marion, you might want to bear that in mind. So we're going to talk about hot air balloons first, which is pretty fun. The following is the silliest picture of a hot air balloon that I could find on the internet, so I thought that was pretty silly. It was pretty good as far as silly pictures of hot air balloons. And the thing about hot air balloons, the last lecture we talked about how if you put helium inside of a balloon, then that will cause it to float, and we talked about why that is. But with a hot air balloon, there is no helium or hydrogen involved, it's just hot air. And so how in the world does this actually work if all you have is hot air to work with? So, and as you know, in a hot air balloon you have some burner, which burns natural gas or something and heats the thing up. And basically, the thing to realize is that the air pressure inside of the balloon is actually the same as it is outside, approximately the same. There's not a huge difference between that inside air pressure and outside air pressure, but it's much hotter, and so ideal gas law being what it is, if you have something that's at the same pressure as cold air, but it's hotter, the only way that that can be true is if the density of that air is lower, right? Because the pressure is proportional to the density times the temperature. And so that's part of the magic of hot air balloons. So once upon a time I was Googling around and I found this interesting equation for the lift that you get from a hot air balloon. Some people like to write hectopascals, which is why there's that HPA. You'll see that sometimes. But this is the equation that you come up with, and so I double-dog dare myself to try to figure out where this comes from and try to reproduce it, and in a couple of slides I'll be able to show you how to do that. All right, where does this come from? Well, if you think about the hot air balloon and the buoyant force, remember that this density is the outside, it's the density of the fluid that's outside of the thing. So when we're talking about helium balloons, this density was not the density of the helium, it was the density of the air outside of the helium balloon. So in this case, this density is just going to be the density of the air outside of the balloon. It's a cold air. That's going to be the buoyant force. And then there's this is the weight of the air inside of the balloon. So we haven't really thought about, the big basket that you sit in or whatever it's called. But this is the weight of the air inside of the hot air balloon. And so we're going to assume that that's most of the weight of the thing, which, I don't know, could be true. But for now, this is just a thing to do. And so since this is the buoyant force, that means that the net force upwards is going to be the density of the air, the cold air, minus the density of the air that's inside of the hot air balloon. Now the density of the air that's inside of the hot air balloon, that's the hot air, and so that's the air that's going to be less dense because, again, the pressure is the same, approximately the same on the inside as the outside. And so we got to run some numbers on what this could be, but thankfully we know the ideal gas law, and so we have some idea for what this could turn out to be. So what I could do is I can factor out this thing. Oh, there shouldn't be a GeV there. Oops. Should only be 1 GeV there. I'll try to fix that in a second. And so, right, so the pressure is the same, the temperature is different. And so that tells us something about what the density is. Okay, so the pressure in is pressure out. Means that the density in times the temperature in equals the density out times the temperature out. Now the Boltzmann's constant is going to cancel from both these things. Should the mass cancel out? That's a question. And the answer is, well, it depends on what kind of stuff that it is. Is it the same kind of stuff outside as it is inside? The same type of fluid, for example? Well, it's air inside and it's air outside, so yes, it would be the same. So that mass should cancel out as well. And so again, we're left with rho in times Tn. If you divide both sides by the inside temperature and divide both sides by the outside density, then you end up with this, okay? This ratio of the density. So we can stick this into here, I believe is the plan. And we get, don't forget that it's much hotter inside than it is outside. So we end up with this, and that's how it relates to the temperatures there. So there we go. And so now I can take this and I think I multiply through by maybe the temperature or something. Can't quite remember what's next. And then this whole thing is related to the mass times acceleration, right? Because this is the net force. And so since we know that the inside temperature is much greater than the outside temperature, that tells us that we're going to have an acceleration upwards. AY is going to be greater than 0. Okay? So in other words, our hot air balloon will accelerate upwards, right? Which is good. More fun than staying on the ground. So another way to derive this, and by the way, this is similar to the formula I found randomly on the internet. Another derivation of this is to say, well, so here again is our the buoyant force minus the weight of the air, and then you can say, well, the density of the outside air is equal to the pressure of the outside air times the average mass of the particles in the air divided by the outside temperature, things like that. So in other words, we basically just use what we know about the ideal gas law to substitute in for these densities. And then we know that the outside pressure is equal to the inside pressure, so we can factor that out and say that it's equal to some P0 here. And so we factor that out and factor out the KB, factor out the M. So we end up with a bunch of constants. There's a volume here, which is the volume of our hot air balloon. And then there's this pressure here, and you get a bunch of constants, which this is almost indistinguishable from what I found randomly on the internet, basically. And it is and it is equivalent to what we had on the other page. You'd have to move some things around, but you can show that it's equivalent. So there you go. So we managed to, we've caught up with Google, which is always a good day, right? Okay, this is what's called a manometer. I have no idea how they arrived upon that name, but that's the name of it. And so this is a picture of my actual basement. And so there's this red liquid here. It's a red oil. So it's almost the density of water, not quite. And there's an opening here, but then this thing is connected to a tube that goes all the way up, I think all the way to my attic or something like that. And as you can see from the level of the water, it's almost as if this pressure down here is more than the pressure of whatever this thing is going up to. And that's because there's a fan that's running all the time, trying to, I guess, push air into the basement, things like that. So this is an important thing because there's a thing called radon. So if you don't constantly circulate the air in your basement, then what happens is that these tiny little, so radon is an actual atom that's on the periodic table, and they will undergo some kind of radioactive decay after a certain period of time. And so when they do that radioactive decay, then if you're around it, then conceivably you could get a higher radiation dose and possibly get cancer. And not only would you possibly die, you would also sue the company, and nobody wants that. So, so they installed these things to try to just be able to check to see if there's a pressure imbalance. Now, remember in the last lecture, I said over and over and over again, pressure differences makes things move, and that's the point of having a pressure difference here in your basement, because it's going to make the air move. But let's talk about exactly how this height factors into how much pressure we're dealing with. And by the way, there's no air passing through here, so it's not as if there's air passing through the tube that goes down through this thing and then over and then up. The oil is preventing air from moving through. I think I just said all these things. But here's the idea. So you have there's some atmospheric pressure plus a little extra, and that's going to be pushing down on our manometer gauge. Now, if the pressure in the room is the same as it is somewhere else, then it's not going to produce a shift like that. But that's going to be pressing down. Now, over here, the pressure, there's still pressure there. There's still atmospheric pressure. It just doesn't have this extra thing there. And so this extra pressure, remember the pressure is the force divided by the area, so this extra pressure provides an extra force per unit area here. So if we multiply by the area, we can see how much it's going to push that down. And so the density of oil is almost 1,000 kilograms per meter cubed, not quite. And so the pressure difference here, the pressure above ambient, is going to be equal to the density of the liquid times G times the change in height, is what that works out to. So that you might find that useful on some of the homework. So this is a link to a TEDx video on a barometer. And I actually think this is a pretty good video, so that's why I decided to highlight it. But we'll watch it together. Hopefully the sound quality on the video will still turn out good. We're not insanely loud.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist, because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
So when you have a barometer, and this one is made of mercury, so at the top is some sort of vacuum, and so you can say that the pressure at the top is 0. And then, right, so 0 plus rho GH, and so there's some pressure at the bottom, which is the air pressure. So that pressure is definitely not 0, because we live at, roughly 10 to the 5th pascals of air pressure. And so that pressure is definitely non-zero, but the height of that is going to be 0. And so setting those two things equal to each other means that the air pressure should be able to push up this mercury up to a certain height. And so, the video talked about doing that with water, and it only goes up 10.3 meters. Well, let's do that with mercury instead of water and see how high it goes up. So water has a density of 1,000 kilograms per meter cubed. If you have a meter cubed of water, it's gonna be 1,000 kilograms to carry, which is a lot. And so the video talks about 10.3 meters. Well, if you consider this equation, solve for h here by dividing both sides by rho and g, ends up being about 10 to the 5 divided by 10 to the 3 divided by another factor of 10. So that ends up being about 10, as mentioned in the video. If you do this with mercury, mercury is about 13.5 times denser than water. And so it should be 13.5 times shorter height. So again, you divide both sides by rho and g. So this is your rho, things like that. And you end up with 0.78 meters, which is probably not that memorable of a number, but you might have heard of 780 millimeters. So a lot of times pressure gets reported in millimeters of mercury. And my friends at Wright-Patterson Air Force Base, in spite of the fact they have no mercury in their experiment, they still think about the pressure in these units, and the number of millimeters that it would push mercury. So I believe 760 millimeters is sort of the standard temperature pressure. This is 780, but in any case, this is how you come up with that number. And this is why the mercury doesn't go as high. And these two numbers are the same, right? So a millimeter is 10 to the minus 3, and so this times 10 to the minus 3 is 0.78, right? Okay, let's talk about a siphon. So this is pretty cool. So if you start a liquid flowing, and sometimes you have to kind of like suck on it to start it going, the liquid will go up through this tube and all the way down. There's limits on exactly how high this thing can go, which I'll talk about in just a second. But this is the effect, that the fluid can lower its center of gravity by going from one thing to another. Now this is altogether mysterious, I would say. It is helped by the fact that water molecules are slightly attractive to each other, which is why you get things like surface tension and things like that. Which is why when you put your finger in water, then the water like sticks to it, kind of. Yeah, so they're going to get it going, and then they move it to the new cup. So that's part of the magic of the effect, but there are limitations on how high this can be, and the Survey and Jewett homework asks you to figure out how high that can be. So how high can Y be, this tube? And there's some speed here that the water is coming out, some density of the water. Well, the way to think about this is that, we have atmospheric pressure here, but as it, which is going to push water up through this tube, but only so high. And so it can't push it above a certain level. And so here at the bottom, you just have atmospheric pressure. The height Y is 0. And then as you go up, there's the pressure at the top. And if you're going to raise this tube as high as it can possibly go, that pressure cannot be any less than 0. And so you're only going to be able to raise it, that pressure here is only going to be able to push this a certain height. And so you just kind of put these things together, and you say, all right, well, then the max height is equal to the atmospheric pressure divided by rho times G, and that can, tell you what you need to know. So that's part of how you get the answer on one of these things. All right, now vapor pressure is interesting. So this is a little funny, because what I have to do is I have to go back and I have to say, like, well, actually, this was not entirely correct, what I told you before. So hold on tight. But basically, the issue with vapor pressure is that you don't get all the way to 0 pressure at the top. And even if you were to use the most expensive vacuum pumps, and my friends at Wright Pat or on Columbus campus can tell you just how much money you can spend on vacuum pumps. But if you put water, say, in an experiment, if you put a cup of water in an experiment, you pump on it, it's never going to get to pressure 0. Because at a certain low pressure, that water starts turning into a vapor. You can try to suck out that vapor, but if there's a lot of water there, it's going to keep sucking it out until it runs out of water. And so you just can't have 0 pressure with water. That's just not what happens. Instead, what happens is that there's a certain pressure here. So here's a room temperature, right? So water from our faucet is, here we are at 1 atmosphere at room temperature. So water is a liquid here. But if you pump it down, eventually it turns into water vapor at this many degrees. And so there's a certain pressure associated with that. So you're basically never going to get below that pressure if you're going to try to pump this thing down, just empirically. So I just showed you water. So again, you're always going to have some residual pressure up there at the top of the barometer thing or at the top of the siphon tube. And so this is equivalent to this many pascals, so 2,300. It turns out that alcohol has a higher vapor pressure, which I don't know, maybe is why you smell it more. I don't know. I'm not a chemist. Ask a chemist sometime. But interestingly, ethylene glycol has a much lower pressure, and so its vapor pressure is only 500. And so if you want a gas that is going to allow you to get a better vacuum, then you should think about using ethylene glycol, which I believe is part of hand sanitizer. Little known fact. Now mercury has an even smaller vapor pressure, very, very small vapor pressure. And so if you wanted to make sure so the difference from 0 is even less for mercury. But anyway, so these are the different liquids that are worth considering. And by the way, my friends at Wright-Patterson Air Force Base doing their laser experiment, they used to use water under the highest vacuum that they could, which had to stay above this thing. Then later, a year or two ago, they switched to ethylene glycol to try to, just for exactly this issue. And so how does this change our barometer measurement? Well, it means that for a mercury barometer, instead of having a vacuum up here, we're going to have this very small pressure. So at the top, the smallest this can be is 0.26 pascals, so you get this. And so then, that's equal to atmospheric pressure. So atmospheric pressure, 10 to the 5 minus 0.26. I think we can all agree that's basically 10 to the 5. So you get the same thing as before. But with water, you might get something slightly different. So the pressure at the top is now 2,300 pascals. And so when you solve for that, you have to subtract these two things. You get slightly less. You get closer to 10 instead of 10.2, something like that. So it is a small effect. But I believe in some of the homework questions that ask it has you have to think about this. Yeah. All right, now we're going to talk about fluid flow, which is a whole nother class of homework problems that you'll have to deal with. So this is one of my favorite things. So here's a fluid flow demo that I'm going to go ahead and open up. Let's see if this works. Behind me is one of my favorite visualizations.
Yeah, it's crazy. There's dots, man. What's going on here?
Okay, so here's the thing. So what you have to do is you have to draw a pipe. So my laptop happens to be a touchscreen laptop. So I highly recommend using a touchscreen. You can use a mouse too. That's fine. It's a little harder, but the best thing is to literally just sort of take your finger and kind of connect all the dots, like you're in second grade again. So there you go, looking good. And this is going to demonstrate fluid flow. I'm sorry, I'm casting a shadow on the board here.
Well, I would definitely pass second grade if that's what it takes, drawing dots.
That was amazing, Liv. All right, so here you go. Now the next thing you do is you got to press the space bar here, and that's when the fun begins. There we go. So there's some objects that are flowing through. And right now, there's not a whole lot of stuff inside of this pipe. And so what you can do is that you can just sort of press the screen. So you can click the screen or press it, use the touch screen, and that will add more objects to it. And what you want to do is you want to fill up this pipe with these objects. Okay? Now, if you look closely, you'll see that maybe the average velocity here is maybe 4.6, 4.5. But the average velocity in the middle is more like 6 or 6.1. And if you just look at it, let's just look at it for a second. Okay? So is it believable? So Liv, you got to tell me if this is believable, Liv. Does it look like the things in the middle are moving faster than the outside, or is that just?
Yeah, I would say they look like they're moving faster for sure.
I mean, at least a little bit faster. I mean, it's like 4 versus 6 or something like that. But it actually is moving faster. And so this whole thing is what I think of when my kids go in the backyard and they get the garden hose and they start spraying each other with it, And what's the trick to get the garden hose to spray across the backyard?
I would typically put my thumb on the hose and then go like that.
Yes, exactly.
Get wide coverage.
Right, and the reason that works is because you're constricting the flow. So you have all this water that wants to go through that garden hose, and that nice big garden hose, but when you put stick your thumb into it, there's only a small little space that water can squeeze around. That's what we're doing here. There's only a certain amount of space for that water to get through, whereas the rest of it is quite large. And so the water ends up moving faster here than it is here because it's all squeezed. And there's all this water that's sort of piling up and pushing this stuff forward so that this stuff ends up going faster. All right, so here's the idea. So you have a certain amount of fluid flowing into this thing, and then it's more constricted. The fluid keeps on flowing. And so first question, what's the volume of a cylinder? Well, it'd have to be the cross-section area. The area here is going to be pi r squared times the distance. So it's going to be the height times the area is the volume. And what's the flow rate? Well, there's a certain speed, so that's or is it change in volume per time? So how much volume is entering this thing per time? And so this is this delta V, let's say, is the full volume, and this delta T is how much time it takes to replace that volume with a new set of fluid. And so that whole volume is going to be the area times the height. And then the thing to think about, we're talking about replacing the water here over some period of time. Well, that height divided by that period of time is, if you think about it, the water is kind of steadily flowing. It's just going to be the velocity, and so the flow rate is going to be the area times the velocity. The units make sense. Seems to make sense to me. The faster V is, the bigger A is, the more flow you get, volume per second. And so, if you want to think about how much mass comes into it, so you have some density of water times how much area, how much volume you've got there. In some period of time, this amount of volume moves through this first part. This is sort of like cylinder 1. This other thing is cylinder 2. And so you have some area there, some volume, and the same thing over here. You have some density here, some volume here, and over some period of time, delta T, you're going to have a certain amount of volume of water moving through, and it's going to move through according to how fast V2 is moving. And the key thing to realize is that if there's a certain amount of mass of liquid moving in, that same mass of liquid has to leave as well, because we're not going to store up like water like a squirrel here. We're just going to keep on letting it flow through. And so if those two things are equal to each other, and the time interval is the same, of course, then you end up with this equation, which is true quite in general, but for water, water is incompressible, and so the density is not going to change. Is the fluid incompressible? If it's water, yes. Then you set the densities equal to each other. But if not, so for example, with air you'd have to use this. But if the densities are the same, you end up with this. And then you can solve for V2, for example, if you know what V1 is, things like that, which is nice. Okay, but if not, then there you go. All right, now here's a brain teaser for you that is going to help us understand a new equation we've got to wrap our minds around. How much energy is in and how much energy comes out? So if you think about the kinetic energy of the stuff coming in, well, there's a certain amount of mass coming in that has a certain velocity, so that velocity is squared, that mass coming in. By the way, this is the kinetic energy over some period of time, so maybe it's like a second or something, how much kinetic energy comes in 1 second. And then you could ask the same thing, how much kinetic energy comes in 1 second, or how much kinetic energy leaves in 1 second over here. So you know there's a certain amount of mass that leaves in that second. It's got to be the same as over there. But it's leaving with a different velocity than it is on the left. So you know the masses are the same. But if it's water, we know what this V2 is going to be. So I can sub that into there, like so. and I can solve for KE out. I get this, which is weird because it means that the kinetic energy out equals the kinetic energy in times this factor. And here's the question, what's bigger, A1 or A2? Well, this is A1, that looks pretty big. A2 is smaller, right? The area is smaller. So this A1 over A2 is going to be greater than 0, and then square it. And so we're going to have more kinetic energy leaving the system than went into it, which is madness, right? What in the heck is going on here? All right? But this is actually correct. I'm not trying to argue that everything we've done up to this point is invalid. I'm just pointing out that the kinetic energy coming out of it is going to be more than what went in. And so the question is, where did this energy come from? Is the question. So is this a perpetual motion machine? Well, no. The question is, where did this come from? And what could it have come from? And a related question to this is, what is the pressure inside of this part of the pipe? And how does it relate to this pressure here? Well, a related question to this that may help us is that what are the units of pressure? So far we've been talking about pressure in terms of newtons per meter squared, but think about this for a second. Is newtons per meter squared equivalent to joules per meter cubed? Yes, it is equivalent. So 1 joule is a newton meter, so a joule per meter cubed is a newton meter per meter cubed, which is also a newton meter squared. Okay? And so these things are equivalent to each other. And if you think about the unit joule per meter cubed, that's kind of an energy density. It's the energy per unit volume. And so maybe we've been thinking about pressure all wrong. Maybe pressure is actually energy per unit volume. It's not force per unit area. Or maybe it's both things. So if you think of it in terms of energy per unit volume, then it starts to make some sense. In terms of that, maybe what we've really done is that extra kinetic energy, we took it from the pressure, because the pressure is energy per unit volume, and so maybe we took that extra energy from the pressure, and basically the pressure, thinking of the pressure as a random, there's random motions associated with the pressure, right? So they're going every which way. And so what we've done is we've taken that random motion and we've diverted some of it to overall flowing motion is all we've really done. And so we haven't necessarily violated conservation of energy, we've just come up with a different thing. So when you think of it this way, and you think about the change in pressure, well, you get something like this. And so this pressure is we can use this as the change in kinetic energy divided by the volume, because remember the pressure is the energy per unit volume. Well, it's going to be something like this. So the kinetic energy out is more than came in, and then divide that by the volume. You are going to find that P1 is going to be greater than P2. So this pressure is going to be less than that pressure because we stole energy from it. Okay? So the pressure is going to be lower. And in fact, if you go and measure the pressure inside of this thing, you'll find that it's lower. So we can do this a little bit more quantitatively and do something like this and say, all right, well, the mass divided by volume is going to be the density. And so the mass divided by the volume of these cylinders is going to be something like this. And so we end up with this, which gives us that. And this is Bernoulli's equation. Okay? And so it tells us how much lower P2 should be based on how fast the things are moving in that second pipe. Okay? And we can go ahead and generalize that equation in a second. One interesting example of this is that my friends at Wright Pat had this water nozzle, and they were pushing it faster and faster. They wanted to get the water to squirt out as quickly as possible because they were hitting with the laser and they wanted the target to refresh very quickly. But they found that eventually, once they pushed it hard enough, it would freeze. And what was happening is that the velocity was so large, the pressure drop was so. This pressure was dropping so much that the temperature was dropping too, and so eventually the water nozzle would freeze and would just turn into ice. And so that's one of the examples of Bernoulli's equation. Others examples, sometimes people point out that when you're next to a semi-truck, you can sometimes kind of get sucked towards it. That's Bernoulli's effect. It is something that comes into play on the wings of airplanes, although don't expect anything along those lines for the final. It's a pretty complex thing. But it does come into play in our daily lives. Like even in terms of hurricanes, we talk about the strength of a hurricane in terms of the pressure difference. Well, why is there a pressure difference? We have all this spinning stuff. It lowers the pressure, it raises the sea level because the sea level doesn't have as much pressure pushing down on it. And so at the end of the day, the measure of the pressure of a hurricane tells you just how significant the winds are, just how high the seawater rise is going to be. Which I know in Ohio does not mean too much for you, but I grew up in Florida. My parents grew up in Ohio, but I grew up in Florida. So it's an important thing. And so this applies to any kind of incompressible fluid, water, oil, most liquids, things like that. So technically, if it was up to me, I would only give Bernoulli's equation things for liquids. So if you notice here, I have rho being the same here. Sometimes people apply this to air, and you can apply it to air, but it's a dangerous thing to do because what if the density of the air here is 10%, 20% different than it is over there? So strictly speaking, this is true of liquids, but some people like to apply it to air as well, and gases. So when you add gravity to the mix, it's very similar to before. You have water flowing in from one place and then going to another. It might be at a lower elevation. And so once again, the volume of water in has to be the volume of water coming out of it. It's incompressible if it's water, so we don't have to worry about the density there. So we know that the velocities are related like this, like so. And so if we combine this with what we just found for Bernoulli's equation, we'll find that this is true, which seems reasonable. Again, I'm treating the densities the same on both sides. Some people will apply this to air, and I think they're a little bit crazy, but sometimes it does work for air as well. But there's a danger that the density won't be the same there, is the point. If you can play around with this demo if you're interested. Now, one question that you have to answer in the homework is, or at least the survey and geo homework, is this, which is if you have some flow rate. Now, earlier I didn't talk so much about the flow rate because we didn't know that there was this term here, but now that we know, technically there is some 1/2 rho v squared term going on here because this water level is decreasing, but it's probably doing it pretty slowly. And so usually you can neglect this term if it's wide enough. Or at the very least it's slow compared to the water that's zipping out of this little pipe here, right? And so so this is the pressure there. You still have the atmospheric pressure on the surface of this thing. So that's not zero. So that equals 10 to the 5th newtons per Pascal. At the top, there's some pressure here. Rho gy, you have the 1/2 rho v squared. That does have an effect on the pressure. And so probably this pressure is going to be, I believe it's the same as it is on the bottom. So that will cancel itself out, like so. And you end up with this, and you can solve for what v would have to be. And so the larger the height, the larger the height difference, the faster that the fluid will flow out. So there you go. And that about covers it for this lecture. So I hope this was helpful.